We're talking electrical components tonight. Okay? So we've already talked about resistance. So how many electrons in the outermost shell does a, so remember, if y'all remember when I was talking about that, we had 3, if you had between 1 and 3, what did you have? 1 to 3 electrons in that outermost shell. So if this is my nucleus, in that outermost shell, if I have between 1 and 3 electrons, what do I have? Now you have a conductor. That's what I'm trying to get at. Between 1 and 3 is a conductor. You add in that 4th electron, you have what's called a semiconductor, which means it kind of conducts, it kind of doesn't. It's all right at doing its job. Resistance should have between 5 to 8 electrons in that outermost shell. If y'all remember back to middle school or 9th grade physical science, we call that a what? Call it a happy atom, right? Because it was an atom that was complete, it liked itself, it was electrically neutral, it was all good. That's why water, pure water, should not conduct, because it's a happy atom. Because at any one time, the hydrogens and the oxygen atoms are complete. They have those 8 electrons. Okay? The whole premise of resistance is that it's an opposition to current. So what does that mean? It means that if you have a river and you have a dam on that river, you have an opposition to current. Okay? You are opposing the flow. You're opposing the current. And how many of you have ever seen a space heater? Actually really looked at it? The reason it's called a space heater is because this is space. Supposed to heat a big space. Not because it's in space. Seriously? Bad joke. I penalize you for that bad joke. That's a dad joke, dude. I'm going to throw a flag on the play. That's a dad joke. So if you've ever seen a space heater and actually looked inside it at whenever it's not on, you see coils of what looks like wire. What that is called is resistant wire. When you run a current through it, it becomes really, really hot, which helps throw off all the heat. By the way, you're not supposed to put that near anything flammable or near cabinets with flammable, combustible materials. It was. It was not me that did it. Don't worry about it. I'll tell you later.
Okay, we talk about like what Barry Allen did?
No, but similar.
I don't know.
We're not talking about that. All right, so what we have is called dissipation. All right, anytime you run current through anything, it's going to heat up and and if any of you have ever been close to those old TVs, or if you've had your computer on for a long time, and you put your hand on the bottom of that computer, what does it have a lot of? It's got a lot of heat. Because energy can never be created nor destroyed. Y'all remember that law? So, in the case of electricity, we dissipate it through heat. Okay? So when you have the two forces of current and resistance fighting, it gives off a lot of heat. That's why computers have fans. It's why you have to keep a lot of things really cooled. The supercomputers they keep trying to build, I think they're called quantum computers. Currently, the whole reason they're having problems with that is because you have to basically keep them in a refrigerator to keep them cool enough. Otherwise, they fry themselves out. Huh? Yeah. Well, if you use your phone too long, it gets hot, right? I mean, seriously, have you ever been on your phone all day and then you actually put your hand to the screen? It gets a little warm. Okay? So power that is produced in an electric circuit, the power that is produced is dissipated as heat in most cases. That's why if you've ever seen, if you've ever had to change out a light bulb, especially after it was just on, yeah, you can and sometimes will lose your fingerprints. Yeah. What? Well, the whole thing about a fan blowing cold air is that you're not looking at the electrical source. What a fan does is it pulls air through it to cool it. But you're not actually in touch with those electrical components. The electrical components that cause that fan to turn, the motor and all that, oh yeah, that can get hot. That can get really, really hot. But generally, the fan, in the way it's pulling that air to it, cools itself. Um, okay, let me try and. I'm trying to think about how exactly I want to say this. That's a totally different system. That's a horse of a totally different color. Okay, because the way that's set up is what? Well, the whole meaning behind it is, and the whole history behind it was that people used to sell off horses, but because people couldn't read, they would get the papers for the horse, go up to the horse, and what you're expecting to be a black horse was either a white or, patchy colored or whatever. That's why they call it a horse of a different color. So, quick little side note on that. God, y'all get me distracted sometimes. The way that HVAC works is in and of itself not what you think it is. Okay? Most of the control systems that you control remotely control what the input and output are. And it has a lot more to do with hydraulics and pneumatics than it does with electricity. Mm-hmm. There's a lot of it to that, yes. If you really want to talk about HVAC, speak to an HVAC student. Or we have a department up there that they can explain it far better than I ever could. But essentially, that it does not have one thing to do with the other. Okay. Something like an electric fan in your house or in your room, that's one thing because it's got a little motor on the inside. Or the ceiling fan in your room. That's got a motor of its own. And both will produce quite a bit of heat if they are left on too long. Your HVAC units, totally different thing. So, talking about energy and energy dissipation, so energy is the capacity to do work, okay? We measure it in what are called joules. We'll get into that in a minute. The rate it's used is called power, and power is measured in watts. And the story behind that is quite interesting. So, how many of you have ever studied anything about the steam engine? Okay. The initial steam engine was made by Thomas Newcomen, who made a very simple steam engine. Then this guy named Watts comes along and pretty much improves it by over 50%. He found ways to make it better. So whenever they came down time to, so they named power after him. That's why it's called watts. But the whole thing about power is that it's equal to energy divided by time. So the energy you use in your house over how long you use it is how your power bill is actually conducted. How many of you have ever seen your power bill and actually gotten a really good look at a power bill? What does it build to you in? Not kilowatts. Kilowatt what? Kilowatts per hour. Kilowatt hour. We'll kind of talk about some of that. Back whenever I was working retail, a woman comes up into our store and says, "Hey, I need help finding a toaster." And so I took her down the aisle that had all the toasters, and she said, "Well, what is the real difference between these two?" I said, "This one's 1,000 watts, this one's 1,200 watts. What that means is one's going to get hotter than the other, but they'll also affect your power bill." Yeah. That was a long time ago.
Show them where it should be, and then you tell them again, okay, show me how it should be.
I work at Tuesday morning, which is basically an everything and anything, you never know what you're going to find kind of store. Yeah. All right. Not right now. All right. So what we have to go with Ohm's law is what is called Watt's law. So Watt's law is not, so if you remember Ohm's law, I'm going to do a little circle, V-I-R. Watt's law uses voltage and current in the same, pretty much the same way. So whereas Ohm's law uses voltage, current, and resistance, Watt's law takes voltage and current from Ohm's law and uses it to find power. Kind of interesting, right? So if you have an appliance and you know what the current it draws and you know what voltage it draws, guess what you can use it to find? What your power bill's gonna be. Something like a refrigerator or something like a washer or dryer. You can use these to find out exactly how much draw it's going to be on your house and give you a power bill estimate. For something like a fridge that runs perpetually, just assume it's 24/7, 365, right? You can tell exactly how much power it'll eat up in a year. Okay? So, we already kind of said this, but power is used over time, and we measure it in watt hours. This is what the power companies bill you with. By the way, anybody know what power company this side of Bessemer gets? Huh? It is not Alabama Power. This school is not on Alabama Power. They're not. Nope. Nope, it's nothing to do with Southern Company. It's TVA. Tennessee Valley Authority. And there is quite a backstory to that. I'm not going to tell you right now. So, Tennessee Valley Authority. No, short version is Tennessee Valley Authority came about. They were the main power company for Tennessee. Alabama Power formed separately. And that's about all I'm going to say on that right now. Because there's quite a rivalry between Alabama Power and Tennessee Valley. You can look it up. It is very interesting, but I'm not getting into it tonight. Very true. So yes, a lot of Bessemer is powered by TVA instead of APCO. So, a watt hour is found by multiplying the power used by the time in hours. So if you use 120 watts of power for 30 hours, you get 3.6 kilowatt hours. So how many people know what some people will do to take it to the extreme? So what a lot of people do to kind of save power and take it to the extreme, they actually will unplug everything in their house, except for like the most vital things. They turn off the HVAC and everything else because it saves them power. Personally, I think it's a little crazy, but if you really, really want to be crazy, all you really have to do is go cut off the main power. That'll save you money. But it will also take every last bit of power out of your house and reset everything in your house. So, yeah. But supposedly, you use power just by having things plugged in. Doesn't matter if you have them turned on or not, you use power by plugging them in. Personally, I want to see exactly how much residual power are you actually using by having that plugged in. And is it really worth unplugging everything in your house before you leave every day? I don't know who came up with that whole setup. I would love to know, just so I could sit there and ask them, how much power are you getting residually from this? Well, I'd kind of like to know that too. I would love to know exactly what voltage those cars charge at. And I would love to know exactly how long it takes, what current it has to pull. That's going to equal up to a nice sized power bill. By the way, any of y'all know what most of the power in Alabama comes from? Nuclear. There's about five of them, I think. There might be six. In very remote places, like Foley. No, not Foley. Yeah, I think there's one in Foley. Funny enough about that though is the fact that most of it still runs on steam power. Nuclear is basically running steam power. Huh? I don't know off the top of my head. I know that there are ones. They just opened a new one a couple years ago. I think that was the one in Foley. Huh?
Car, it costs you 13 cents per kilowatt hour. So it's about $9 to charge a car with a 200-mile range. Fully, yes, from complete. $9. Yes. So
Only including how much it costs to actually get that charge.
yes, on top of that, we don't know. But it's like
Yes, but the question also is, where do you recharge it whenever you are not home? Yes, you have a 200-mile range on those electric cars, and so and then you have to sit there and figure out who you can beg into letting you hook your car up to charge it. So let's get back to this, guys. I know. So the resistors we've been using in lab. Let's focus. Focus. The resistors we've been using in lab. Okay, and believe it or not, there are resistors the size of us. They're generally used on giant oversized equipment, things like overhead cranes that in order to begin moving take a heck of a lot of power to just start the motors. Okay? So resistors are rated in two things, and you definitely want to write this in your notes because it's going to probably be a great question one day. Resistors are rated in two things. They are rated not only for what they can handle as far as resistance, but they are also rated for power. So a light bulb is rated for power. If you exceed that power, what does the light bulb do? It pops. If you have a light bulb that is greater than the power that the socket puts out, what happens to the light? It's very, very dim. So with that in mind, the power rating is what is guaranteed as the maximum amount that the resistor can dissipate without damage. A light bulb is a resistor. So whenever you plug in a 120 watt light bulb into a 150 watt socket, what's going to happen? Every time, it's going to blow, right? However, if I take that 120 and plug it into a 60 watt socket, what's going to happen? It's going to be very dim. It's going to be overpowered. So the power rating is the guaranteed maximum that you can put on this without damage. Okay? This is determined by the physical characteristics of the resistor. For light bulbs, it's what is the material. For resistors, we also not only look at the material it's made of, but also the physical characteristics of it, the size and the physical sizes of it. Best way I can say that. Yes. This right here is probably the best thing you can write down because I can guarantee you that that is probably a question on a test. What, am I saying it too hard? Hint, 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 hint. Yeah, but that would be really hard to keep moving up and down to sit there and go hint, 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 hint. Okay? So the physical characteristics are what determine the power rating of a resistor. Now, what do I mean by that? Well, I mean that I will not say this is a true thing across the board, but in general, the bigger the resistor, the more wattage rating it has. Okay? So something like a space heater, or like I said, they make resistors as big as me to go with industrial sized overhead cranes. They make resistors even bigger than that. The reason they are so physically big is because the current that they must draw through them is a truly massive current to just get these cranes started. Okay? And if you don't have a good enough sized resistor on that, what do you think happens? You're liable to blow up your resistor. But it's all about the wattage rating that they're looking for with these, not so much the resistance rating. Some of those resistors don't have a resistance more than about 5 ohms, but their wattage rating can be 500 watts. That's how much power they're putting out. But the size of it is also looking at how much current draw is it using. Because some of these can be hooked up to quite a bit of voltage, quite a bit of current, and if you don't have something that's got enough power rating to it, you're going to still blow it. So just kind of keep that in mind. Yeah. Depends on the overhead crane. They have some, like, let's take US Steel, for instance. If you've ever seen how it's made, when you've ever seen how they make steel or aluminum or any metal that they are going to later sell as ingots or anything, they have buckets that probably 3 to 5 of us could stand in that they pour metal into. We're talking liquid hot metal. And then they have to turn this thing upside down so they can pour it into molds. Yeah. You're talking cranes that can haul tons and tons and tons of not only the bucket that has to be made of metal that is metal and or compository materials that are strong enough to stand up to liquid, hot, steel, or aluminum, but you're also talking something that has to hold the material that goes into these buckets full of liquid, hot material. And then has to pull that up. That can be upwards of several tons of material that is hauling. So you're talking a crane that has to be, the crane itself could just about be the size of this room. We're not talking the support post or anything else. We're talking just the crane, the thing that is moving. So, and then you also have smaller cranes that are used for nothing but maybe picking up pallets and moving them from one side of a factory floor to another. They make smaller ones that are only like a 1/2 ton or 2-ton crane. Each one's going to have its own draw as far as power, okay? Because the power needed for it to move, let's just say we need it to move along the tracks. That power draw is going to be the most of it because what it takes to move, let's say something the size of this room, think about what that would take, okay? That would be like asking you to push a car versus a semi-truck. Yeah, you want to take the car. So how much power do you have to use to move the semi-truck? You have to use a heck of a lot more versus a little tiny car. So that's why I said it's not really a cut and dry question on that one because there's literally a range of sizes that these things come in. And so each one needs its own power requirements to fulfill. So, did that answer that question, or did I go overboard there? So we have two different types of resistors, and one is called a fixed resistor. That's what y'all have been using so far. These guys up here, those little tiny things. And then you have what's called a variable resistor. These are made of carbon composite, generally, metal film or wire wound. But variable resistors, there's a couple different things. I'll get into those in a minute. Yes, they're carbon composite. So we'll get into that in a minute. So some of the typical fixed resistors, these guys right here with the color bands should look familiar. We're actually going to be talking about the color code tonight. The rest of these you generally do not see very often because they're mounted surface chips. Now what does that mean? That means that if you pull out any computer's board, that's where you're going to generally find these, and it's not really something you would mess with on a day-to-day. Yeah. You're talking about this one? The next one? That is what people typically think of as a computer chip. Generally, those are either pushed through a circuit board or they are mounted to the surface of one, but they are soldered in place most of the time. We actually get to play with those quite a bit. I'm talking about these right here. Yes, they're bigger. Wish I knew where the one that works with the heat gun was, but I don't know where that one is right now. Mm-hmm. I have. Not exactly a PlayStation, but believe it or not, I have torn apart my electronics more than once. Okay, focus. Focus. What is the actual question here? Whenever this speaker went out at home, this was actually mine, if I can find the other part of it. All right, so this one's actually a better example. So this is a small printed circuit board. No, the gold in these are very minimal. But you can see the different little surface mounted chips. That's why you don't really see these a lot. These are really hard to replace. That's why you don't really see them a lot unless you are really into computer repair, which most of the computer repair places are closed these days. Because why? No, because it's cheaper to replace than it is to repair. Kind of like it's going to eventually be cheaper just to replace a whole car than change the battery out.
Oh yeah, hey, my battery went out in a Tesla, 15 grand to replace it.
Yeah, pretty much. And that's just the price for the battery. That's not counting what they would have to do to break into the whole car and get to where the battery banks are.
What happens when a lithium-ion battery runs?
They short out and catch fire. Mm-hmm. That's why you don't. I'm not a fan of Tesla because they have not made something that is truly sustainable. Anyway,
Going back to the traditional AA battery, that's not an actual battery, it's a cell.
it's a cell. It's a single cell.
Yeah.
Yeah. That's why they used to be called an A cell, a D cell, a C cell. They were actually called cells. They were not called batteries. Batteries came about because the term battery got into um, your typical household, and instead of, excuse me, and instead of being able to correct it, it just kind of grew into being the term it is. Now they are called batteries simply because the term got into mainstream media and everything else. It's not, have you got a cell or a triple A cell? It's, do you have a battery? Like a lot of things, right?
Yeah. I guess it's because somebody started using the term that they started calling them batteries, and then the next person started.
It's kind of like people that sit there and say, turn on the juice whenever they mean turn on the power. Oh, God, don't do it. Don't, you don't want to have the lecture. Believe you me. So yeah, don't ever do that in front of Nancy. But if you hear it in movies, what do they call it? They say, turn on the juice. Don't sit there and go say, turn on the power. It's one of those things of pop culture starts meeting
Or better yet,
terminology.
I got another one.
Hmm.
When somebody says, "Give me a clip of magazine," and they're talking about a magazine,
Yeah,
we no longer use now.
it's where pop culture meets trade talk.
Now, if you're talking about a whole magazines are not clips.
Yeah,
That is my pet peeve. Is that when I hear, "Hey, I need a clip here," so you know, your gun takes magazines. It doesn't take clips.
yeah. Well, a lot of that becomes terminology meets pop culture, and pop culture don't care. It's kind of like if you've ever seen movie physics are crap. How many times did Mythbusters disprove movie clips? I think that was like half of their episodes, right?
Just like, or it's like one of the biggest things. If you shoot a thing of gas,
Yeah, no. But because movie culture loves to put that out there. And yes, Mythbusters did actually disprove that if you shoot a gas tank, it will not explode. Yes, Hollywood likes to lie to us. But anyway, it leaves a hole in it, and that's it. Okay, let me put it this way. I'll go ahead and disband all this right now. Gasoline, how do you like it?
fire.
No, you're lighting
The fumes.
the fumes. You're not lighting gasoline.
Wasn't it somebody who told me that you could take a cigarette and put it in gasoline and shoot
You
it out?
can. You can. Gasoline lights by fumes, not because what you have to have is the correct air to fuel mixture for it to actually go off. So the way the physics of Hollywood works never would work because there's not enough air inside a gas tank to allow for an explosion. There are three things you need to have fire. You have to have oxygen, you have to have a fuel source, you have to have a heat source. Bullets don't give off enough heat to allow for that to be your heat source. There's not enough oxygen in a fuel tank for it to actually mix right and cause the explosion. I don't know.
Yes, I mean, theoretically, that's the explosion, right?
But at the same time, with any kind of fuel, you still have to have the right air to gasoline mixture. Whenever your car is running, the way it works is that you actually have nozzles that spray the fuel into where your spark plugs are. And thus, whenever the fuel gets put in there, it's mixing with air. So whenever the spark plug ignites, it blows up, essentially. You're creating mini explosions with those spark plugs. It blows up the gasoline, which causes uh, the cylinder to move. It forces the cylinder down. That's why it's called a combustion engine. So that is why you will never really have an explosion. Kind of like if you ever get on YouTube and you see people trying to light off gasoline, generally they're not lighting the gasoline, they're lighting the fumes, and if they're really not careful, they tend to light themselves.
Fireworks forcing around and they hit it in the middle and they explode everything. You can't see them after that.
You're dealing with black powder at that point. That is not gasoline. Let's not go into that. If you're dealing with fireworks or anything to do with fireworks, you're generally dealing with black powder and mixtures of black powder. All right, guys, focus. Focus. Back to what we're talking about. Back to what we're talking about. It can wait till after class. All right, so we have two types of fixed resistors. No, these are not to scale. If you come and look at the circuit board I have got right here, you can literally tell that they are not to scale because the smaller one is T90, less than the size of your pinky nail. The other one is not. So with our basic resistor, and believe it or not, if you've ever opened a TV, if you've ever opened anything electronics, you will find generally that they have resistors somewhere on one of the boards. And they will be these types of resistors, metal leads and all. So the resistance material is a carbon composition. Why? Because it works really well at doing so. You have an insulation coating around it to help maintain and not give off over much heat. Because if electronics give off too much heat, they can actually overheat. And y'all have probably seen what happens when that does. It's never good. It's kind of like your phone. What happens if you overheat your phone? It starts to what? It starts to fritz out and freak out before it starts really causing damage to the phone. So the other one you have is a surface mount chip. And again, it's got its resistance material here. It's got ceramic. And most of the time you have these things that are just too small to see, but you soldered them to the board and they do what they need to do. Now, what I kind of want to point out is that resistors are not unidirectional. What is unidirectional? What do y'all think that term means? Unidirectional would mean one direction. Resistors are multi-directional. So in other words, it doesn't matter which way you plug it into a circuit, it still works. There is no forwards or backwards bias to these. They work both ways. However, I will point out on the color bands. Those can only be read one way. We'll talk about that in a minute. All right. So this one is a metal or carbon film with a helix to it. This one's a resistor network. These are some wire wound ones. Now, there was a really cool one that used to be up in motor control's room. I don't know if it's still there, but it used to be a giant wire wound resistor that you could actually move it back and forth on, and it was what's called a potentiometer. So resistor color codes. Because resistors typically are smaller than your pinky nail, we don't really want to mess with trying to stamp numbers and everything into them. So what we do instead is we have created what's called a color code. Okay, we have what's called the color code. It starts with the color black, moves to brown, and then you have, how many of you remember the rainbow green bib. Everybody remember that? What it stood for was red, orange, yellow, green, blue, indigo, and violet. Right? So we have black, brown, red, orange, yellow, green, blue, violet, gray, and white. Now they've done several mnemonic devices to this. This is the one we provide. If you go on the internet and decide to try and find a different one, that is up to you. Just watch what you look for. Guys, like with all mnemonics, some people have taken it to a not so correct way of saying things. Huh? So the one we typically give everybody is big, beautiful roses occupy your garden, but violets grow wild. There are other ways to remember it. I took the first letters of each one. So you have BB. This is kind of how I ended up remembering it, because you do have the rainbow colors right smack dab in the ever-loving middle of it. I memorized the fact that that rainbow starts with the letter 2. You have black and brown to begin with, gray and white to end with. This is the way I memorized it, just because that's the way my brain worked at that time. And still works to this day. So your rainbow color starts at the number 2, ends at the number 7. You have gray, which is 8, white, which is 9, black is 0, brown is 1. And I just kind of worked my brain around that. Whatever mnemonic device or method you use, you might have to work to do so yourself. Because I'm not sure what might work for everybody, because everybody has a different way of memorizing things, right? Kind of like whenever I first had, never mind. I'm not getting into that. No more off topic tonight. Nope, I don't want to get off topic again tonight. So, huh? Okay, not worried about PLCs. So we have the base colors. These are fairly typical of every resistor. Most resistors you come across have between 4, now let me revise that. You have between 3 to 5 bands of resistance. Okay? Band 1 through 3 are generally, well, back up. Bands 1 and 2 are number bands. What that means is that if I match band 1, brown, to the number that's 1, black, band 2, that's 0. Band 3 is a multiplier band, so that means I'm going to multiply 10 times whatever band that corresponds with. In this case, it's red, so I have a band of 2. So I have 1, 0 times 10 to the 2, and band 4 we'll explain in a minute. So what this ends up being is a 1,000 ohm band setup or a 1 kilo ohm. And I'll explain the last band in a minute. Now, one thing I will say about these bands is that it will never start with the color black. Because just like you do not write a number as 0, 1, 0, and you're trying to write the number 10, you're not going to start your color bands off with the number 0. Does that make sense? That is a hard and fast rule. If you ever see a number band starting with the color black, it does not exist. It will not exist, and that's all you need to put on there is DNE, does not exist. Okay? Does that make sense to everybody? All right. So additional colors. So in the multiplier band, there are 2 other colors that you can put there, and they are gold and silver. Now gold, they tell you multiply to the 0.1. I say multiply by 10 to the negative 1. Silver is multiplied by 10 to the negative 2. That is a far easier way to write this than sit there and say, well, multiply by 0.01 whenever you're doing multiplier bands as 10 to the 2. Why not make it as 10 to the negative 2? It makes it far easier to remember and you don't struggle as much. Does that make sense? Then you have what's called the tolerance band. Now, the tolerance band is very interesting because the whole reason it exists is because manufacturers like for it to exist, and we as electronics people like to have it. It gives us a little play. So, do you think a 120-watt light bulb, let's say it's 50 ohms, do you think it would be exactly 50 ohms across the whole production batch? No, it'll be close. It'll be within a range of it, but it will not be exactly 50 ohms. So that tolerance band allows for manufacturer error, but it also allows us to have a little bit of playroom whenever we're dealing with resistors. Makes it to where the tolerances for the creation of a circuit don't have to be so tight. So it kind of works in a couple of different ways. All right, guys, it's 7 o'clock. I'm going to give so you have a multiplier band of gold or silver. That's -1 or -2, 10 to the negative 1 or 10 to the negative 2. Far easier way to remember it. That magnet. All right. And then you have the 5-band resistors. So the -1 and -2, the tolerance bands of gold, silver, or if you have no tolerance band, you get a tolerance of 20%. Those are really big tolerances. If you have a gold or silver, this only applies if you have a 4-band resistor, by the way. If you have a silver band in the tolerance, that's a 10% tolerance. Quite a big margin of error, which we'll talk about here in a second. If you have a gold, it's only 5%. A lot of the ones we use around here are gold. Fairly tight tolerance. Now, if we have a 5-band resistor, that's where these colors come in. You won't generally see gold or silver. And before I get to that, let me go ahead and say this. A resistor will never start with 3 colors. I already told you it will not start with black. It also will not start with gold or silver. Okay? So if you think you're looking at a gold or silver band to start with, you have to flip the resistor the other way and start from the other side. Okay? A resistor will never start with black, gold, or silver. If it starts with any of those 3 colors, you need to just say no. They don't exist. If you start with black, that's like starting with 0. Gold and silver, you're probably reading the tolerance band first. Flip it around. 5-band resistors. The tolerance bands for 5-band resistors, if you have red, that's a plus or minus 2%. Brown is plus or minus 1%. Green is 0.5, blue 0.25, and violet is 0.1, or 0.1%. Okay? Does that make sense to everybody? Is everybody good? Everybody got that written down? Yes. So what a tolerance band is it basically gives you a range. And we're going to talk about that here in just a second. We're going to do some math here in a second. You got that for me? All right. So a tolerance band gives you wiggle room. All right. So, thank you. A tolerance band gives you wiggle room. So you have 3 different types of resistor color band sets. You have 3 bands, in which you have a digit multiplier, and your tolerance is plus or minus 20%. Okay. 4-band, you have 2 digits, the multiplier, and the tolerance is going to be probably gold or silver. Now you can get red or the other colors in that tolerance band. So those can appear. I do have some resistors that have 4 red bands. We'll talk about what that might mean later. But the 4 bands run digit multiplier tolerance. The 5th band just adds another digit. So you start out with 3 digits, multiplier tolerance. You will always have a tolerance. You will always have a multiplier. The number of digits depends on if you have a 3, 4, or 5 band. And of course, I'm dropping everything tonight. What happens when I get klutzy? All right, everybody good? All right, moving on. So color coding resistors. So just to kind of give you an example of what I mean, we'll do B together real quick. So first of all, the first color is brown. What number does that correspond with? Brown corresponds with 1. Black, 0. Brown means times 10 to the what? To the 1. And silver is plus or minus 10%. So what that would look like physically should be 10 times 10 to the 1 would be 100 ohms plus or minus 10%. To find the tolerance, okay, to find the 10% tolerance, you're going to go to your number. You're going to know that your decimal is ending here and move it forward 1 place. So you're going to be saying 100 plus or minus 10. So your upper limit is 110. Your lower limit is 90. If your resistance, when you measure it, falls between 90 and 110, you have a good resistor. If it falls outside of those parameters, it is not a good resistor. Okay? Now let's talk about what that means electronically. Okay? What that means electronically is that if I need a tight run of resistance, I'm going to be real careful what I choose. If I choose a silver band, that's going to be quite a bit of tolerance between it. What I might look for instead is something along the lines of a violet tolerance band, which is only 1/10%. Okay? If I do not need a tight tolerance, 10% is a pretty good resistor. Okay? Means I got a little wiggle room to play with. I don't really have to deal with something that's got to be exactly 100 ohms. It means that I can have a little bit of play in those resistors. Just to kind of tell you what these other ones are, you have red, violet, orange, silver. This is a green, blue, green, gold. I'm going to give y'all a few minutes to see what y'all come up with on your own as far as these 4-band resistors. If you remember, the first 2 numbers are going to be digits. The third will be a multiplier. And the last is your tolerance. Okay? Yes.
Can we go ahead and call it silver or gray?
What?
Because you got one of these silver, so I can just call it gray.
No, it's silver. That means that's the tolerance band, and the tolerance is 10%. I'm gonna go ahead and give y'all worksheets that correspond.
More and more studying.
Yes, more and more studying. More.
Do we have to turn them in?
Yes, before finals.
3 weeks from now. What?
The last four studies.
Any term ends up there.
Before finals.
Oh, so how many before finals, I can just remember? It's this one, and I know you gave us one.
There should be 3. Powers of 10, Holmes Law, and the census. 5 of each, or as much as you want to do.
Oh, wow, so only 5, we don't have to do 5.
You have to do a minimum of 5 each page.
Okay, that's more. That's twice the work.
Your favorite one.
Twice the work. I know you can do it. No.
And I'm copying you a little bit of help here. I'll copy out real quick. Make sure everybody gets a copy tonight. So, real quick, looking at this. Back to what we're doing. What's the number for red? Violet. Orange is 10 to the what? And silver is plus or minus 10%. So this is a 27 kiloohm plus or minus 10%. Just to kind of show you a quick way that you can do the 10%, because again, 10%, you're just moving your decimal place forward 1 place. So this should actually be, whenever you're doing for your 10%, the short way I tend to do it is 27.0 plus or minus 2.7. The reason I do it this way is because I know I shifted that decimal place forward 1 place. That's what happens when you multiply by 10%. So I should have an upper limit of 29.7 and a lower limit of 26.3, if I'm right. But not 26. Don't pay attention. Should be 24.3. So what that actually is 29.7 kiloohms and 24.3 kiloohms. That is the upper and lower limit. What I'm giving y'all is a chart, a bit of a cheat sheet, really. Okay? It gives you the color code breakdown, and it tells you how to do between 4 and 5 color bands at a time. Okay? It quite literally does the full breakdown as well as how to do so. Did everybody get one? You make sure you got one. I printed exactly 7 because I knew there's exactly 7 people in here. So there should not be a leftover in my hand, except for my original. I've already got a copy. All right. So now, looking at C, I'm going to erase all this before we go to the next portion of this. Looking at C, we start off with green. What is green? Blue? Green is 10 to the what? And then plus or minus 5%. Because silver is 10%, gold is 5%. Look at your sheet. Down here at the bottom, it says gold. Multiplier is 0.1. You might want to put in there as well 10 to the negative 1. The other one is silver. 10 is multiplying by 0.01. What you might want to put inside that is 10 to the negative 2. All of these are just multiplying your bands. But if you look at the tolerance band, gold is 5%, silver is 10%. If you have no tolerance band, in other words, a 3-band resistor, it is 20%. So translating 56 times 10 to the 5th into proper notation is 5.6 times 10 to the 6th plus or minus 5%. Okay? Everybody following so far? So how do I find 5% of 5.6? Multiply it in your calculator by 5%. There's a different way to do it, but I'm not going to tell you because it is more complicated. Should be 0.28 if I remember right. Am I correct? So let me pull up my little calculator here and see if I'm down for a second. Where's the percent? Oh, why is it over there? Okay. Yes, it should be 0.28. So So 5.6 plus 0.28 is 5.88. This would be 10 to the 6 is mega. This book, mega. Subtract that out, it should be 5.32 mega. So what it has to fall between is 5.88 and 5.32 mega ohms. So there's two ways to find 5%. You can multiply it in your calculator as 0.05, or you can do it the way I just did it. Multiply it by 10%, so you move that decimal place forward and get your number, and divide that by 2. Except that one's a little more complicated. I would stick to just multiplying it by 0.05. So. And I just now really figured that particular way to do it out. Been trying to experiment with that little technique, but sometimes I get mixed results. All right, is everybody good with this before I erase it and we put up the neater version of this? Everybody good? No questions? Anybody want to take a picture real quick? Nobody want to take seconds of it? Huh? Okay. Just so you have photo records to go with your notes. I know sometimes that can help. Huh? A good example. This is what it looks like whenever the teacher does it on the board. Now let's go to what it actually can look like in a neater format without all the scribble scrabble. A little bit of both. I'll probably have about a couple of questions on the paper portion where you would have to physically do it. And I would have them as multiple choice online. So you definitely want to be able to do it both ways. Yes, I know I'm evil. Well, ha 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 ha. Right there. So if you look, we have red, violet, orange, silver, which gives us 27 kiloohms plus or minus 10%. The upper range is 29.7, the lower is 24.3. Now, if I put an ohm meter to this and read it as 30 kiloohms, is that a good resistor? No, it is not. Why? Huh? It's beyond the tolerance. So put it to you this way. There's a different way to think of this. If you're measuring a piece of wood, because you're trying to build something, everybody's done that, right? Measured a piece of metal, measured something. Measuring tapes have a bit of tolerance in play themselves, right? Because it all depends on how well you hook that metal into something. And if that metal end comes loose, it all of a sudden gives you a lot more play, right? But at the same time, you're still trying to cut a piece of wood. If you cut too long, in other words, if you cut something like 30 kiloohms, that's too big. That is outside the range you need it. If you cut too short, let's say you cut 23 kiloohms, that means that you're going to be outside your tolerance and whatever you're building will not work. Correct? So that's why you want to fall inside this tolerance. You want it to be long enough to fit what you need it to fit, but not too long. You want it short enough to fit, but not too short. The Goldilocks set. You don't want too big, you don't want too little, you want it just right. Straight down the middle. And looking at C, which is again the one y'all did, if this fell out to, let's say, 5.9 mega ohms, would that be acceptable? Nope. What about 5.3 mega? Be too short. What that Goldilocks? Does that make sense? I figured that analogy would help out a little bit. I've given 1,001 analogies trying to tell people exactly what it means to fall in between. Then it's good resistor. So that would be like cutting your wood perfectly to that measurement. It's still good. I mean, I know I'm not answering what you think I should be answering, but that's exactly how that works. Is that, okay, so whenever you are cutting a piece of wood, right? Let me change this over to blue. Black ink doesn't show up as well. So if you're cutting a piece of wood, so this is your piece of wood. I'm sorry I can't draw straight lines on a board. So this is your piece of wood. You need to make your cut right at this line, right? If you set your saw and you need, the wood you need is this bit right here. Okay? If you cut right on the line, that is perfect. However, if you set your saw a little more to the left or to the right, it's not going to really kill the project, but it means you're going to have to work a little bit harder with the project. Does that make sense? So the general tolerance when you're cutting wood is somewhere in between, kind of like that. And it's like a close-up of it. That's the same thing for these guys. As long as it falls within these tolerance ranges, you're good. If you start getting outside into this area or this area, that's where you're going to have problems. Does that make sense? Does that answer your question? Okay. Sometimes the whole reason I ask if it answers your question is because sometimes I get a little off topic. No, me never. And I want to make sure that I actually answer the question instead of going completely around the bend, completely around the barn, coming out the other side, and you're still sitting there going, you didn't, this did not answer what I was asking. Yeah. Because yes, I have sometimes a little prone to that. Life happens, right? So on a 5-band resistor, so now that you have the chart in front of you, this does include both a 4-band and 5-band set. You can use it to help you with this next set. Because instead of 2 digits, you have a third digit. That's all that's really different with this, is you have a third digit. Okay? So you end up with 3 digits, your multiplier, and your tolerance. All right. So this one is red, violet, black. This one is also yellow, red. Now the reason I'm kind of putting these up here is because I know for a fact the further away you get from this board, the more the colors look a little strange. The red kind of looks very pinky. Brown tends to blend out. It tends to not look as easily done. So this one starts with yellow, black, red, black, brown. This one is orange, orange, red, orange, green. I'm sorry that does not look great, but trying to get them up there. I'm going to give y'all just a minute to work on those, and then we will see how close you get.
At least, and I can't just ask. So we have in total.
We'll get you through.
No problem. All right, guys, we're doing 4 labs a day. We got this.
Yes.
We don't got this, Rich. I don't know. Some of these books.
Some of them are very short, some of them are very long. Believe you me.
Well, some of these have, the next 4 we have 2 activities each.
Exactly.
Which I'm guessing those are the long ones. Well, no, not really, because the lab that they're doing now has to do with relay diagrams. skip 6'3", which 6'4", you don't really do the programming until the very end. Maybe each one of these labs is like, well, all the labs are 50 points each.
Hunt, focus on this stuff.
Oh, I am. I got my cheat sheet somewhere around here.
Okay.
Sorry. Mix matching. It's the only time I focus on.
All right. So, have y'all at least gotten A done? I'll give y'all another minute or two, and then we'll kind of start going over these.
I just add them together.
All right. So, looking at A, guys, I'm going to go ahead and do this one real quick. That is what you should be looking at to begin with. That is the direct translation of what this is. Now, putting this in engineering notation should give you 2.7 mega ohms plus or minus 2%. Because red is 2%. If you look on your paper, in the tolerance section, follow red over to it, and you get 2%. I will go ahead and tell you this, guys. In the multiplier, what you might want to do is kind of scratch out all that because that's going to confuse the crud out of you. Where it sits there and says, where it says in the multiplier 1, 10, 100, 1K, 10K, I'm not worried about those. This 10 multiplying by 1 is 10 to the 0. This is 10 to the 1, 10 to the 2, 10 to the 3, to the 4, 10 to the 5, 10 to the 6, 10 to the 7, and 10 to the 8. Yeah. I think that's supposed to be 10 to the 6. 0, 1, 2, 3, 4, 5, 6, 7. Yeah, should only be 10 to the 7. So. why 1 gig's not added. So you might want to just write beside them 10 to the something, because that's what you're actually doing. The multiplier band should look more like the 10 to the something, because that's something you should be more used to at this point. Okay? The reason I say that is because it makes it a lot less confusing in the long run, if you want the trace. Because the way they have it laid out here would be that this would be times 10K. Well, that's great and all, as long as you remember that 10K has a different way of saying itself. I like 10 to the fourth better. Why? Because 10 to the fourth is something I'm more used to dealing with, and I can put it very easily in engineering notation. I don't know what to do with 10K, because what you would have to do is not only write out your terms, so what you would have to literally do if you're using that 10K on there would be 270 times 10 kilo, and then multiply. Once you've multiplied that out and figured out all that, you've got to circle back to it just being 2.7 mega ohms. I like working with 10 to the fourth better, just because I don't have to go back and really play with my numbers that much. Does that make sense? The less I have to mess with this, the better, right? Let's go back to doing lazy math. Let's not make it overcomplicated. Follow the keep it stupid simple program here. Don't overcomplicate it. Huh? Yeah. I like my way of saying the KISS principle better than anybody else's. At least that way I don't insult somebody. Because if you insult the wrong person with saying that, they can get mad at you. I like saying it my way just because it's an easier way of putting it to people. Well, like I said, it just means I don't insult somebody I shouldn't. So 2.7 mega ohms plus or minus 2%. When you multiply 2.7, so when I say multiply 2.7, I am not discounting that the actual written out number of this is 2. But that is not the actual number. I'm just saying I don't want to deal with that number. I'm saying I don't want to enter that particular number in my calculator and have to calculate it from there. What I'm saying is I'd rather work with 2.7. So when you multiply 2.7 times 2%, what do you get? What is 2% of 2.7? 0.054? Okay. Then at this point, I might use this little set of numbers, 2,700. So that means I'm going to be doing 2,700 plus or minus 54. What I'm actually dealing with is 2,700,000 plus or minus 54,000. That's what I'm actually dealing with. I'm just shortening it up and getting rid of a bunch of those zeros. Why? Make it a smaller number, right? Don't want to deal with all those zeros. Do they actually help me add value to this particular problem? Having all those zeros? No, because all I'm going to do whenever I add and subtract those is just end up with the same zeros, right? They're not going to help me with actually solve the problem. So what I tend to do, just kind of pretend they don't exist for a minute and just bring down my values at the end. Does that make sense? So if you find yourself in a bind and you have problems with some of this, you might go ahead and write it out to help yourself with any confusion. Like I said, I tend to shorten things up. I tend to shorten things up just a little bit. So the long version of this would be 2.754 mega ohms to 2646 mega ohms. And yes, I did all this. I would at least do 2 digits. That's fine. Just simply because most meters will only show you 2 digits anyway. So you can kind of round off, but be careful when you round. Does that make sense? So let me just kind of put it out there as a reminder. What is the rule of rounding? Yes. 4 or less goes down, 5 and above goes up. Okay? That is the hard and fast rule of rounding. A lot of people tend to forget that in the middle of a test or in the middle of anything. Keep it in mind, okay? Keep it in mind. All right, has everybody done the other two? Yes, no, maybe so. Need a minute? Is everybody okay with A? I'm going to go ahead and erase some of this. Not yet? Okay. I'm going to eventually stop dropping this. Everybody good? All right. So, somebody tell me what the breakdown of B is. Okay. So we end up with 402 ohms, plus or minus 1%. So what would be my upper range of 402 with that 1%? 406.02. What's my lower limit? 397.98. We'll check those here in a minute. So you would have what was your add and subtract? What was your 1%? Huh? So 4.02. Was that what you said? Okay, so 4.02 is what you added and subtracted. So I gave you 406 and 397.98. Okay. So what you're multiplying, so the way you're getting your tolerance, there's a couple different ways. 402 times 1%, you can do it like times 1% in your calculator, or you can do it as 0.01. So that's just translating it into from percentage to decimal, right? Yep. Then to get your upper and lower limits, you just add and subtract it back in. Does that make sense? You add and subtract it. So you take the 402 that you just found, you add it to and subtract it from your base number. Does that make sense? Okay. So C, orange is 3, red is 2, times 10 to the third, plus or minus what is green? 5%? No, that should be 0.5. Well, I never use 0 in front of my decimal, so. Never use it. So you add and subtract what now? Mm-hmm.
And then I multiplied it to get my 5%. So I did, or,
So you would have multiplied by 0.005.
well, yeah.
Okay.
And I got 16,600. Well, wait, my answer was 332,000.
Yes. So
It says 5%, 332,000. No, yeah, which is
should be 1.66 that you're adding and subtracting.
Oh, so you're removing the zeros.
Yeah, so try and get rid of the zeros because the zeros end up just kind of
So
causing.
see, I did it with the zero.
I understand. So yeah.
So
So
if I
it's
put so 1.66 is 16,000, but without zero. Yeah, so one.
not 16,000. It should be 1,660. That's why it was not sounding right to me because you were a zero too high. Okay. So when I multiply that, because I just put that in my computer, and I have the calculator app open on my computer. It's the reason why I had to go back and try and translate that because the numbers are right, but instead of multiplying by 0.5%, you were multiplying by 5%. So that's why that one was sounding real strange to me and why I went back and checked it. So what you have is 332 with 3 zeros behind it, and you're adding and subtracting 1,660. Now that's 0.5%. It's half of a percent. So if you look at green is 0.05, 0.5. Yeah. Well, yeah. So when you add and subtract that, all right, does that make sense to everybody? So you gotta make sure you double check what you're adding and subtracting, and yes, I will let you use this particular page on your next test as a cheat sheet. Because I'm not that mean. But it is something y'all need to go ahead and start working to memorize. It's because is everybody good with this before I erase it?
Oh, you're talking about the very last color?
Well, yeah, so the last result we're looking at, you got orange, brown, red. So the browns are just like a filler, it's just there.
Wait, what do you mean?
Talking about, I think,
Which particular one are you talking about? Because I don't know that you're seeing brown where.
See, this looks like a brown, but then you see this looks
No,
like
the
a
brown is the brown is the base color. That's just the base color of what the resistor would be because resistors come in several different ways. The ones we typically use are tan color underneath. That doesn't mean anything. Yes, they come in green, blue, brown, tan.
That's a good question.
Yeah. So I see where you're going with this. No, what you're looking for are the big wide bands. And if you remember actually messing with resistors for lab the other day, how they had the color codes or the colors very brightly marked. That's what you're going by. You're not going by the base color of the resistor itself. All right. Erase all that real quick. And we're going to check everything we just did. If I can find my mouse. Okay. Wait. Somebody did not do their math right. For A. No, I did not make this PowerPoint. That was somebody else. But this particular problem right here is one I'm going to have to make note of because I think that's yellow, but right now I think they meant that to be gold, which that means I need to change that color. That is not gold. That is yellow. Yeah, a little bit of color difference, but that can also be due to other things. So I'm going to go back and see what I can do to fix that. That or I'm going to put a little box on the top of each of these and write out what the color code, the colors actually are. Because that's annoying. All right. So we already went through that one. Really? All right. So let's talk about resistors that are not, how do I say this? They have the potential to be changed. Okay. There are two of them. One is called a rheostat. And in your book, it says that it has 3 legs. The truth is it has 2. Excuse me. one that has 3 legs is what is called a potentiometer. And when we get to lab next time, that's one you're going to get to play with. The potentiometer. Otherwise, somebody told me once that they used it at work as what's called a variable speed control. If you remember the old radios or any of the old electronics, it was whenever you moved it one way, it ended at one point. If you moved it the other way, it ended at that point. But you could not move it further than what it ended at. Y'all know what I'm talking about. The old radio dials, volume dials, your oven, all sorts of things used to use them. These days we use a electronic version of it that translates it a little bit differently, but I'm not getting into that because that is a totally different topic. Okay, so the way these work, okay, I'm going to go ahead and tell you how a potentiometer works. You get a signal, the full resistance runs between the 2 outermost legs of a potentiometer. That is the full range of resistance. So if I have a 1 kilo ohm potentiometer, I'm going to read full resistance between legs 1 and 3. If I want to vary the resistance and get a variable reading on that resistance, I have to look either between 1 and 2 or 2 and 3. Because 2 is connected to this particular mechanical thing, which is called a wiper. And what that wiper does is as it moves, it's changing it has the ability to read a different resistance as it moves. So if I was to get it between legs 1 and 2, the further I turn it towards 1, the less resistance I have. The further I turn it towards 3, the more resistance I have. So let me grab one real quick so y'all can kind of see what I'm talking about. So this is one of the potentiometers you will be playing with in lab. You can see I've got 3 wires to it. It's got a dial to it. So as I move it one way, depending upon which lead I'm looking at 2 and I'm either looking at 3 or 1. And as I move it, my resistance values will change depending upon where this wiper is connected between that resistance. Does that make sense? That's why whenever you turn the volume control, the more you turn it one way, the louder it gets, because the resistance would have been either more or less depending upon how the setup was. And if I turn it the other way, the volume turned down. That is why that works that way. Any questions on that? No? All right. So this is the difference between a potentiometer and rheostat. One has 3 terminals, the other one has 2, versus what the book says. Both can be wire wound, but potentiometers can also be carbon composite. These guys run very high resistance. Believe you me, I've seen a potentiometer the size of this table. They're big. They can get small, they can get big. Rheostats have lower resistance. These guys typically are smaller and rheostats bigger. The biggest difference between these two, besides the legs, is that potentiometers control voltage. These guys control voltage. The other ones control current. Okay? They're both rated according to power. This guy can be connected as a rheostat. You cannot connect a rheostat as a potentiometer. You can't conjure a third leg no matter what you do. And you will often hear these things called pots. Okay? These are often called pots. P-O-T-S. Why? Because saying potentiometer too many times, you tend to get a little tongue-tied and it starts sounding really weird at times. You call it a pot, fast, easy, quick, and done. Okay? So the main big ones here is that potentiometer is a voltage device, rheostat controls current. You can connect a potentiometer as a rheostat, and that they have 3 terminals versus 2 terminals. I'll go ahead and pick that information out for you there. Okay? Not on hand right now. I've got to go dig. I would have to dig one out. Not too many. Well, you should be finishing up here in a minute. Well, I say not too many. We're probably going to stop here in just a little bit. We still got 20 minutes of class time left. I'll help you in a minute on that. But let's, yeah. Everybody good with this? All right. So these are a couple of different ones that are sensitive to light or to heat. The thermistor is sensitive to heat, the photoconductive cell to light. Both of them have their uses. We'll kind of get into those another day. We've kind of talked about conductance. So this is another kind of talk about it. It's the opposite of resistance. It's basically if you cut water in your hand, that is resistance. What water you hold, you're resisting the urge for it to move through your fingers. Yes? But no matter how you cup your hands, how much water gets through? It's eventually going to get through your fingers, right? What gets through would be the conductance. It's what is able to move through it. Okay? So most material will allow current flow, especially under circumstances. It's measured in Siemens or Mohs, and it's the inverse resistance as far as formula. It's what we were talking about the other day. Any questions on this before? The biggest one about this is that the formula for this is the inverse of resistance, and it's measured in Siemens. Okay. And that's represented by a giant letter S, an uppercase S. Everybody good? Anybody need a second? Okay. Because we're going to talk next about something that we use quite liberally in the world, and that is capacitors. Now, capacitors are mostly used in AC because they charge and discharge according to frequency. Okay? They have the ability to store an electrical charge. We use them a lot. They're also one of the more dangerous items used.
That's technically right.
Yeah.
I do that so my coworkers will go search it up like faster than they find the price. That'll be popular. I just want to see if I was like technically right for calling that because I knew their job.
Yeah, that is what they do. They're basically voltage regulators. So the interesting thing about capacitors is they're used, let's say if you're talking about Alabama Power, they're used to keep the line voltages steady. So you don't end up with sudden spikes of voltage hitting your house.
Oh, I didn't know. I thought those were the transformers' job.
The transformer's job is not to regulate voltage. It steps it up and steps it down depending upon what's needed to get it down the line. So what a transformer does outside your house is take like thousands of volts and make it 240, 120 for your house. Capacitors just keep it at an even state.
So can we see how they look like, or they're like hidden, like in the?
Capacitors? You don't want to get in here one of these. The voltages that these things deal with would be enough to fry somebody. It's bad enough that these things store voltages and oh yeah, if you don't discharge a capacitor before working on it, you gonna hurt something. Mhm. Yeah, capacitors are not something to play with. There are people that do play with them, and they're not smart for doing that. Capacitors are one of the items that I was watching the other day about. They're talking about Tesla's death ray or the death beam. The way that they were building it was creating banks of capacitors that they were charging up so that they could discharge it in a stream of lightning. It would basically create man-made lightning because you could charge these, and the ones they were using were military grade, and they still blew one up because the capacitors are that finicky. Yeah, pretty much. Man-made lightning. These can also be called condensers, but these guys are used to regulate voltage in electronics. Okay? They're very, very common. You also have inductors. Now, inductors are how to say inductors? They store energy not so much inside them, but in an electromagnetic field. And again, they work with frequency, huh? Yeah, they vary on frequency. They're also called a coil or a choke. You might have heard them called that. They're also one half of the next thing. The next thing is really fascinating because they're transformers. These are used to increase or decrease AC voltages. That is their only job. And no, they're not transformers, robots in disguise. Don't say it. Don't say it. I just did it for you. Yes, I know. Everybody thinks of Transformers, and everybody thinks of the movies or the TV shows or the little toys. No, these things are the giant three-pronged things that sit outside on a pole that bring voltage into your house. I wouldn't know anything about that, but okay. Yeah, well, transformers are very dangerous devices just by the fact that on one side you can have thousands of volts, on the other side you're dealing with 120. Now that's voltage. That is what forces electricity to move. That's not the current. And it's not generally the voltage that'll kill you, it's the current. Because that'll fry you on the inside out. Okay, let's pause the story. We'll get to it in just a second. We've got like literally 5 slides left, and I want to make sure we get through them. Okay? So then we have what's called diodes. Now, you might have heard of diodes as an LED, light emitting diodes. These allow for energy to move one way. You also have transistors, integrated circuits, there's a lot of these. Diodes are one of the most common ones that you see visually with electronic circuits. Why? Because they're the thing that lights up and shows all the pretty colors. Okay? But they are a one-way device. They do not allow flow in the opposite way. They're used frequently with AC. You have electronic instruments. We've dealt with these. The most common one, you don't really see voltmeters, ammeters, or ohm meters separated out of a multimeter. Why? Because it's just easier to combine them into one. You also have what's called an oscilloscope. You don't really see these used much in the field, but what they allow you to do is see what kind of signals you're getting from places like the power company. Okay? You have what's called a power supply. Power supplies take AC voltages to DC voltages because you do not want AC voltages in your electronics ever. Why? Because if they spike, they will fry out everything you have. Yeah. This helps regulate the AC voltages to DC voltages so you don't fry out everything you own. You know, don't fry out your computer. It's always a bad thing. Well, if you have even with a surge protector, you can still fry everything. That's why they created power supplies, is to make sure that instead of taking just straight AC power, you have a way of keeping it to DC power, and if something fries out, it doesn't fry out the whole thing. Okay? All right, so you have a manual ranging meter, which you can, as you can see, you have to twist the dial to get to where you want. These are very common, pretty cheap. You have auto ranging, which just kind of move through the sections on their own. Oscilloscopes. All right. So if y'all got any questions on this chapter or on things we've covered so far? No, oscilloscopes are used for complex circuits where you need to have a certain signal coming out. They're generally used more with integrated circuits and it's a test equipment. It's more test equipment than actual anything else. Trying to think about how to say this. I can build a circuit see if I can find a circuit that's already built one day, and I can show you what an oscilloscope does. Basically, if I was to hook the oscilloscope to look at what Alabama Power sends us, I could see the differences between the high and lows of voltage. Okay? This thing lets me see voltage change over time. Does that make sense? So that's all it is. It's just a way to see voltage changing over different sets of time. Okay? All right. Any other questions? Huh? That one? All right. So things to know. Resistance we've talked about. Dissipation happens as what? Heat. Types of resistors we've covered tonight. We've covered 4-band and 5-band color codes, what power is, voltage, current, resistance, and their relationship to power. DMM stands for digital multimeter. You have rheostats and potentiometers as variable resistances. Okay? All right, so we have one more lecture, maybe two, I think, left. And then we will be done with lecture. Now, we need to probably do lab next week. We will more than likely go over test 2 on Thursday. Okay, so make plans for both of those guys. We'll probably end up with test 3 week after next. I'll have to check on our dates. I try not to have our final and our test 3 right next to each other because it kills people. I'm going to count roll here in just a second. Digital multimeter.